Distinguished colleagues and guests, good morning. It's April 6th, 2021, 10 a.m. Moscow time. We're beginning the panel session for the defense of the thesis by Evgenii Ievlev. The thesis is submitted for the academic degree of the candidate of sciences in physics and mathematics. Their specialization is 010402, theoretical physics. The topic of the thesis is dynamics of non-Abelian strings in supersymmetric gauge theories. Under the order issued by the Academic Secretary of St. Petersburg State University, Alexander Gniatov, as of January 14, 2021, number 163/1, I, Alexander Andrianov, Doctor of Sciences in Physics and Mathematics, Professor of the Department of High Energy and Elementary Particles Physics of St. Petersburg State University, was appointed the chairperson of this dissertation board, and the order also approved the candidacies of the members of our board, and let me introduce them. Sergei Afonin, Doctor of Sciences in Physics and Mathematics, Professor of the Department of High Energy and Elementary Particles Physics of St. Petersburg State University. And the following members of the board are working in the remote mode. Viktor Petrov, Doctor of Sciences in Physics and Mathematics, Senior Researcher, Head of the Theoretical Physics Department of the Konstantinov St. Petersburg Nuclear Physics Institute of NRC Kurchatov Institute. Victor, do you see us and hear us? Yes. Viktor Novikov, Doctor of Sciences in Physics and Mathematics, leading researcher of the Quantum Field Theory Laboratory of the Lebedev Physical Institute of the Russian Academy of Sciences. Do you see us and hear us? Yes. Yes, I do. Arkady Weinstein, Doctor of Sciences in Physics and Mathematics, Professor of the University of Minnesota, Twin Cities, the United States of America. Do you hear us and see us? Yes? Yes, I do. Okay. And we also have our candidate for the degree, Evgenii Ievlev. And we also have a remote connection with the thesis supervisor, Alexei Jung, Doctor of Sciences in Physics and Mathematics, leading researcher of the Theoretical Physics Department of the Konstantinov St. Petersburg Nuclear Physics Institute of NRC Kurchatov Institute. And dear colleagues who are working in the remote mode, in order to improve the quality of our connection, kindly turn off your microphones. But don't forget to turn them on when I give you the floor. I would also like to inform you that the panel session of the dissertation board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted from Russian into English and vice versa. Currently, we have an email address posted on the page with live broadcast of the board session, and all listeners can submit their questions to Mr. Ievlev online. The questions regarding the thesis and the current academic discussion. And these questions will be forwarded to me by our technical service, and I'll read them out during the discussion. Questions must be related to the presentation and the content of the thesis. And don't forget to give your name and position if you submit a question. Questions that have nothing to do with the scientific discussion or the thesis or the text of the thesis will not be voiced. So under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by local normative acts, the session of the dissertation board is valid, providing 2/3 of the appointed board members are present. And the total number is not to be fewer than 4 people. Our dissertation board consists of 5 people. Everyone is with us today. including 3 members of the board who are working remotely. We have a multimedia connection with all the members of the board, as well as with our candidate for the degree, therefore we have a quorum. And our session should not last more than 2 hours, and the agenda is as follows. First comes the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements, and chairman's answers to questions, if any. Then the candidate's presentation providing an overview and findings of the research, 15 minutes for that. Then questions to the candidate regarding the presentation, no more than 2 minutes per question. The candidate's replies to the questions, 5 minutes overall. Then the reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions. Each board member will have 10 minutes for that. Then comes the chairman's report on the thesis, 10 minutes as well. Then the candidate's comments about the reviews on the thesis and replies to the questions, 20 minutes for that. Open discussion. Anyone present at the defense may state their position or ask questions on the thesis. Yes, for anyone willing to speak out, and I kindly ask you to fill in the registration form and introduce yourself before I give you the floor. Then the chairman will ask the questions submitted during the broadcast via our website. Then the candidate's replies to the questions, 2 minutes per question. Then the presentation of candidate's thesis supervisor, 3 minutes for that. Then a 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. And the discussion of the results of the defense is not broadcast, 5 minutes for that. Then open balloting, vote counting and recording of the results in the protocol. Then we're going to make a decision on whether to confer the academic degree or not. And finally, we will listen to the candidate's closing speech, no more than 2 minutes for that. Distinguished colleagues, any questions or remarks? If there are no questions, no objections. No questions. And no objections, therefore I will proceed. But before we do that, I kindly ask you to switch off the sound on your mobile phones. Thank you. So let me start. The thesis by Evgenii Ievlev for the academic degree of the candidate of sciences in physics and mathematics, the specialization 010402, theoretical physics, is titled The Dynamic of Non-Abelian Strings in Supersymmetric Gauge Theories. The thesis was approved for the defense by the order of the Academic Secretary of St. Petersburg State University, issued on December 24th, 2020, number 11760/1. Mr. Ievlev has prepared his thesis at St. Petersburg State University and at the Konstantinov St. Petersburg Nuclear Physics Institute of NRC Kuchatov Institute. Professor Alexei Jung, Doctor of Sciences in Physics and Mathematics, leading researcher of the Theoretical Physics Department of the Konstantinov St. Petersburg Nuclear Physics Institute of NRC Kuchatov Institute, is the thesis supervisor. So, 5 published works describe the research findings. They include no papers published in peer-reviewed journals recommended by the Ministry of Education and Science, and 5 papers and publications indexed in Web of Science and Scopus. The candidate for the degree has submitted the full set of documents to the academic secretary, and the above-mentioned documents comply with item 12 of section 3 of the order. As far as I am informed, all the documents submitted by the candidate for the degree comply with the requirements and are found in the certification file, and the curator of the defense, member of the Department of Dissertation Board Support, has all the copies. And before I give the floor to our candidate for the degree, I would like to ask you, dear members of the board, if there are any general questions to the candidate for the degree. Is there a need to list the whole set of documents submitted by the candidate for the degree? No questions, okay. Then the short presentation. Evgenii, please, you have the floor. Thank you. Today I would like to deliver a report that is responsible for confinement in supersymmetrical gauge theories. Thesis will consider several aspects of the application of this string. Our goal is to understand confinement in quantum chromodynamics. That is part of the model, and that's quite a complicated task. And the approach that we consider is the study of confinement in supersymmetric cases, considering QCD and other results. And in order to describe confinement, first of all, we should understand the nature and why this string emerges, confining string emerges. Then we should quantize this string and study the interaction of hadrons. And the third step is now not covered by this thesis, and we are going to talk about the first two steps. So all the ideas start with QCD. And as it's not quantum chromodynamics, we have a gluon sector, and we also have, in this theory, U1 calibration factor. And due to supersymmetry, we also have veiled superpartners and adjoint scalars. And we also have hypermultiplet representations, and we have quarks here as well that we're going to call squarks. And we also consider the group with n colors and flavors equal NF. Non-Abelian strings were found here in this theory in 2003 with the participation of my supervisor. Therefore, the development looks like that. If we give our complex scalar quarks using these two indexes in flavor and in color, we can see the following picture. If the matrix of this vacuum expectation values is this one, due to them we see the violation of the calibration group, and flavor group is violated as well, but still we see the survival of diagonal subgroup, and we see the phenomenon that is called color flavor locking. And at that we also have the strings the Abrikosov-Nelson-Olesen strings, and these strings turn it into non-Abelian strings that are characterized by additional orientation levels of freedom. And at that, the instrument that I'm going to use is this 2D, 4D correspondence. It was marked in the late 1990s, and that's a correspondence between the spectra of four-dimensional calibration theory and the sigma model. And this correspondence was described, and this sigma model is an effective theory on the worldsheet of a non-Abelian string. The confinement picture in 4D, this instead of confinement model of mesons look as monopole and non-monopole connected with non-Abelian strings, and in 2D this picture looks like this, kink and anti-kink interpolating between different vacuums of the 2D model. The first part of the thesis is dedicated to the summarization of these developments if n equals 1. How can we achieve it? For example, we take a joint multiplet from scalar and one of the Weyl fermions. We give a mass component here and go to infinity. We see quantum, the shift to quantum chromodynamics, and we also make a decoupling here, and the model resembles the real QCD. And that this does not happen without any consequences. Therefore, it turns out that soliton vortex non-Abelian string is no longer BPS, and BPS is the term that is used to define supersymmetry solitons. And due to, well, the thing is that if your object is a BPS object, then the study of them is easier than the general state objects, and the string stops being a BPS, and this complicates the study. However, you can still get through these problems. And fermion orientation modes that the string had in supersymmetric case, they lift up, get non-zero mass, and they decouple from the theory, and the model turns into a non-supersymmetric one. We don't have the supersymmetry on the surface of the string, and if a quark mass in 4D is different, then we see the potential for internal Boson orientation modes, and this potential breaks down monopoles, and thus this confinement picture remains only in a 0 delta M when quark mass is the same. The more so if we consider the number of flavors that is higher than the number of colors, then soliton string in this theory proves to be semi-local. It has additional modes of the size of the string, and it turns out that during the transition to NO1, these size modes decouple as well, break down, and the string turns into a local string. And then we get back to our case given here with an ordinary local string. First of all, these results were achieved from the analysis of 4D theory, and then we asked a question on self-coordination of these results, and we carried out a study of the 2D effective theory. And on the slide you see a Lagrangian 2D supersymmetric model, and in green you see the components that violate supersymmetry, for example, lambda, nu, member with component with potential, and they happen in 4D, and they violate supersymmetry. And we can study this efficient action when we arise the deformity parameters. And here we should work with mu and change the values in order to check what happens. And we can also consider weak coupling and strong coupling. What does strong coupling mean? The difference of quark masses in 4D. In 2D it plays the role of a full-fledged mass parameter, and if this delta M is much lower than the scale of lambda in 2D, then the theory is in strong coupling, and we can calculate loop effective action, and it turns out that the photon that was introduced to this theory in order to linearize the model is becoming dynamic. and due to it we see a confinement. As was supersymmetry theory, we see what happens when we violate supersymmetry. Photons have zero mass components, and you see the graph of vacuum energy, the graph of breakdown of energy between neighboring vacuums, and we see that at certain mu parameter we see a certain breach. And we make a conclusion that there is a second order phase transition here with a violation of supersymmetry. Then, this theory can study weak couplings as well when mass scale is different. And this theory can study quasi-classical methods. And we observed the following picture: supersymmetry. We had N with a degenerated vacuum, and when the supersymmetry was violated, this supersymmetry is violated, and quasi-vacuums lift up. And kinks in 2D correspond to monopoles in 4D. Therefore, if we lose vacuum, we lose kinks and monopoles in 4D. And we got the full phase diagram of this theory, and that fully supports the results we got in 4D, that weak couplings, when monopoles are lost, and this instead of confinement picture is lost as well. And if delta M equals 0, then two-dimensional theory is always in strong coupling, and confinement remains in this theory. We see monopoles, and 4D theory is in the confinement stage. The second part of the thesis is dedicated to a different model. Let us consider how can we move to super QCD, so with collaboration group U2. And we're going to consider the theory with U2 collaboration group with 4 hypermultiplets of quarks, and beta function is known for sure, and it equals 0. Superconform symmetry is violated by a non-vacuum average quark, and it can be violated with the introduction of mass components, but on the worldsheet theory it is superconformal theory. A non-Abelian string here has 10 levels of freedom for our ordinary ones, and 6 are the internal freedoms. Thus we get a 10-dimensional theory of a superstring. And in 2015, with the participation of my thesis supervisor, hypothesis was offered that in strong coupling we get to the thin string regime, and this string can be studied using the methods of fundamental string theory. And using 2D, 4D correspondence, we're going... Well, we'll consider it later, sorry. And using these methods of the string theory, the spectrum of hadrons was received. Zero mass multiplet turns out to be BPS, a short hypermultiplet. And in this thesis, the goal was to somehow confirm the results, not using the string theory, but working with a field theory. And we managed to do that somehow, and we are going to use this correspondence. What are we going to do? The main instrument is the study of 2D sigma model. Therefore, we're going to study the spectrum of this model, and then we interpret this result in 4D monopoles and in other states. And the study of the spectrum can be studied with weak coupling when beta is much higher than 1. And the spectrum includes perturbative BPF states and also BPS kinks that can be found in classical equations. And these spectra can be juxtaposed with the central charge that we know for this model. For sure, the central charge is a linear combination of ordinary charges. And here you see the formula of the weak coupling. In the strong coupling, we know the formula. It's quite complicated, therefore I didn't give it here on the slide. So we start with weak coupling spectrum and then move forward to the strong coupling. And it turns out that we have a phenomenon, the so-called wall crossing. When we move to strong coupling, at a certain point we see the transformational BPS state. Some states fade away and some remain, and the laws according to which these transformations happen, they resemble the decay laws. Sometimes they are called decay. For example, charge conservation law can be considered here as well, and there is the energy conservation law here that can be considered. And at that it turns out that these curves of marginal stability, they are defined by the equation that the central charges of three particles should be collinear, and this gives us an equation that allows us to find these curves. And that it turns out that gray is the weak coupling, so it's in the far right. When we move to strong coupling, it turns out that perturbative states fully break down, and the spectrum, we see just kinks, the number of, or final number of kinks, and this result is easy to interpret in 4D. These perturbative states correspond to calibration Higgs bosons and screened quarks. And when we shift to strong coupling, you see what happens. And we see the picture that these performative quarks get divided into monopole and non-monopole mesons. And that's instead of confinement mechanism demonstration. And when we shift to a point of beta that equals 0, that goes to infinity, it turns out that in this sigma model it is possible to have yet another deformity. Beta constant is the marginal deformity of supersymmetric sigma model, and when we go to beta equals 0, we see yet another deformity. We can use NRO model to give us the variables, and the determinant in initial model equals 0, but when we go to beta equals 0, this determinant can differ from 0, and this conform symmetry is not violated. And this B parameter is the new parameter of deformity. And where can we take it? It can be either a coupling constant or the vacuum expectation value of a field, and this vacuum expectation value of this short BPS from multiply that was previously found from the string theory. Thus we confirm partially this coordination of the string approach. And also we defined how this state looks like. So that's a state of 4 monopoles, a kind of ring connected with non-Abelian strings, and this state was discovered in 2016. On this slide you see the defense provisions. I've already mentioned them, and the results of this thesis were reported at several conferences, as it was already mentioned. We published 5 articles, and that's the joke that I wanted to give in times of the pandemic. The problem of confinement became a really important issue. So that's it. Thank you very much. Do the members of the board have any questions? Yes, may I? When you talk about the breaking marginal board of stability and got this situation when you have monopole couples, did I get it right? Yes. When you shift to strong coupling, these objects that remain can be used to make up the objects that no longer remain. For example, boson can be made up from dione monopoles, and from these couples we can create upper bosons. For example, yes, have a look at these bosons. They break down into monopole, non-monopole couples, but they don't live by themselves. They're connected by non-Abelian strings, and we get mesons. Yes, but these mesons, do they have a magnetic charge? No, they don't have a general magnetic charge. They have the same quantum figures as in other bosons. So, you don't have these similarities here to get other quantum figures. So you could have made not just these bosons, but also the objects with magnetic charge. Others. Well, in 4D theory, we don't have this additional charge, but it's still we still see the screening here. Therefore, yes, the answer I believe is yes. We just work with mesons. Okay. Any other questions? Okay, let's shift to the speeches of all the members of the board with their reviews and the assessment of the thesis. And I offered to provide answers after each review. As all the reviews were already published on the St. Petersburg State University website, I'll just offer to read out the basics, the basic points and comments to our candidate for the degree. Do you support this idea? Yes? Okay, I would also like to inform you that we didn't get any external reviews, therefore we're going to listen to those reviews that our members of the board prepared. So, Arkady, I give the floor to you. Arkady, do you hear me? Arkady, please turn on the microphone. Okay. I wanted to ask if I could read just the summary. Can I do that? Yes, certainly. Just a second. Okay, I'll find it. Because I don't want to repeat the conclusions of the thesis, because it just takes time and that's it. Because they were already given in the thesis and now we've listened to them in this short review. Therefore, I believe I would just like to read this idea that the candidate for the degree demonstrated good use of the set of theoretical physics as applied to the complicated physics of strong interaction. And I'm sure that Mr. Ievlev is ready to work with further studies. Therefore, I believe that the candidate for the degree deserves the academic degree of the candidate of sciences in physics and mathematics. That's it. Thank you. Thank you. Okay. No comments. Okay. And no answers. Yes, but I can just thank Professor Weinstein for reading the thesis and for providing his review. Okay. Victor, Professor Novikov. Yes. I'll just read the finalizing remarks. The thesis has... I was impressed by the thesis. Yes, I was pleased to read it. It has a lot of interesting results, and some of them... just some of them are enough for the defense of the thesis. And also there is a very good Russian language used in the thesis. There are certain misprints, but I won't just mention them from time to time. There are certain style peculiarities. When the author gives us some literature remarks, and, for example, in chapter 2 he writes, these complicated paths starts here in chapter 2. Well, I believe that's just a beautification of the text, and I certainly believe that the candidate for the degree deserves this academic degree. I did not print out the thesis, but that's the thickest volume that I've ever seen. So just have a look at it. So no remarks here, no critical remarks, none of them, yes. Yes, thank you very much, Professor Novikov, as well, for reading the thesis and for providing the review. Okay. Now I give the floor to Professor Peterhof. Professor Peterhof, do you hear me? Yes, I'm fighting with the microphone. I've already won this battle. Well, the thesis is pretty good, as I believe. And certainly the candidate for the degree deserves the academic degree of the candidate of science. It's really an impressive thesis. Very complicated goals that were resolved in a proper manner. So that's out of question. As for the remarks, I have just several of them. The first remark is on the style. Indeed, it's not that easy to read this thesis, because the author is continuously using abbreviations, and some of these abbreviations are used before they are deciphered. So you just need to have a kind of vocabulary in order to read this thesis and constantly address it in order to find out what do these four letters mean. But that's not a significant remark, but still you should write in a more accurate manner. And what else? Not all the abbreviations, not all the notions introduced are explained at once. It may happen later or before and you've already forgotten it. So that's not a simple reading. But essentially, that's a very good work. But that's an insignificant remark, certainly. And now a few words on the essence that I didn't like. So the thesis is written as a thesis on specific symmetry theories. And still, as it was already mentioned in the goals of the thesis, we're trying to study the real situation that exists in nature. For example, it's wonderful that you managed to imagine an option when the string is type null, and you can resolve it without any conformal anomaly, and you have 10 dimensions. But still in nature it's not the same. Still we have a whale component. No one should be confused by that, because that's low energy theory. and this string is on move, but it does not really help. And if you consider these comments to the width, its width is logarithmically expanded. Yet another example is that we're continuously talking about weak coupling of the monopole, but we need strong coupling and charge confinement. This is a dual theory and it's connected somehow, but still it's useful to understand how these results can be used for quarks confinement. That's yet another style comment. What comes next? And that's not a frequent thing. Few people understand it. That instability of the classical solution does not play an important role. The string should be selected not on this principle, because in real QCD with quarks it's not stable. Therefore, it's not the case whether we have a stable or non-stable solution. And we worked with that some 15 years ago, and we can demonstrate that the strings that such strings play an important role. And such configurations should not be BPS configurations, for sure. Therefore, maybe they were not fully studied in the thesis. Yet another question. Arkady has already mentioned this question in a different context, but still it's unclear for me. Did all the band configurations are confined? And we see that monopoles are really confined. We're talking about weight coupling. That's good. We have a linear potential here. But the question is, don't we have colorless quarks in the spectrum? Now these objects don't have any charge or baryon charge or color, because these events are violated. But still, we can demonstrate that such objects is something that we don't see in nature. Whether it happens in case when n equals 2 or not, and in the continuation of the theory, it's unclear for me. And the last remark that I wanted to mention is what I'm continuously talking about, and we worked on the topic as well. It's unclear for me why the author doesn't use yet another method of study that is applicable to all supersymmetry theory, regardless if n equals 1 or 2. The so-called supersymmetry temperature method. Because in this case, the theory is fully controlled. And there's yet another a theory that considers weak coupling when n equals 2. If the temperature of supersymmetry drops, then we won't have phase transitions, because that's the general characteristic of the supersymmetry theory. Therefore, certain values, especially those that can be calculated in n equals 2 supersymmetry, they remain, and they shouldn't have very significant gaps. What happens in strong coupling is something that we can't find out, but as for Seinberg theory, we can't find anything as well. So there are a lot of works connected with supersymmetry theories, and even in the presentation you've mentioned that. But it would be very interesting to learn how they support the results. Maybe you take one theory and consider it with in strong supersymmetry temperature and compare what happens. So the author also ignores the real QCD. Therefore, he does not consider the spontaneous violation of chiral symmetry. So, as for the confinement, it does not have anything to do with it, but it still would be interesting to study this spontaneous violation of chiral symmetry using the methods that the candidate for the degree uses, and it would be interesting to consider it at high temperatures. And here the situation is aggravated by the fact that the author has the so-called color flavor locking. This Higgs condensate when the color is correlated with the flavor. And certainly it would be interesting to study it, because that is really what we observe in QCD and high densities of material. We do have color flavor locking, as it was discussed. And certainly it would be interesting to compare how it happens in real life instead of confinement situations. It would be very interesting to compare the situations. But still, these are the remarks on the content. They don't make an influence on the importance of the thesis, but they just outline, I believe, the fields for further studies. But still, I believe that the thesis by Evgenii Ievlev fully corresponds with the requirements, and Mr. Ievlev deserves the academic degree of the candidate of sciences, physics and mathematics. That's it. Thank you. Thank you, Victor. So, please, Evgeny, have the floor. Yes? Thank you, Professor Petrov. I'll try to answer as good as I can. First of all, about the Ievlevian component. Certainly that's a fiction theory, and in the natural theory we have it, but it's unclear how to quantize such a string. And in particular, this is one of the reasons why we study what's written in chapter 2. Yes, Professor Polikov is trying to quantize. Yes, certainly there are attempts. Yes, there are attempts. That's what I wanted to add up. Well, not quite successful ones. Okay, yes. But certainly we'll have to deal with that, finally. But now it's considered to consider it without this component. I have 2D sigma model in this case. The thing is that in a thin string regime, certainly there are certain amendments to this theory, but in thin string, that's an exact theory without any amendments. Therefore, we can somehow work with it. And I want to say at once that the study of these supersymmetry theories is quite popular now without direct consideration of QCD. For example, anti-superconformal field theories, they are quite in demand. Therefore, the results that we get here, they're interesting not only to people who are working with QCD, but also to people who carry out some fundamental studies. So as for the choral symmetry, indeed, the thesis start with NOM2 theory. And here we see the interaction with scalars. There is R symmetry, axial symmetry, that can be considered, but this was done in chapter 4. In this kind of theory, we don't have scalars, and we can consider chiral symmetry. And there are scenarios in which we have confinement with violation of chiral symmetry and others. So it's interesting to study it, but unfortunately, right now we didn't manage to do that. But that's a prospect for the study. As for color flavor locking in QCD, indeed, that's a phenomenon that's observed in neutron stars, and we can refer to works of NETA group. And my thesis supervisor with co-authors prepared an article in 2011 on the possible connection of color flavor locking with ordinary QCD. But I'm not familiar with it very well. So it was not covered in thesis. And what Professor mentioned about the instability of the strings, I want to comment on that. Due to the factor in our calibration group, the strings are stable. In ordinary QCD group, the string ends with quarks, therefore it can break down, and we can have a quark couple. Here we don't have the same situation, regardless of how hard we try. So the strings are stable. The first, because you consider glue dynamics. And if you consider material, no, that's instead of confinement theory, and well, and it works a bit different here. Yes, and it's interesting to learn how. Strings themselves can't break down. What else may happen here? It requires additional study. And as for this aspiration to describe the real world, I should say that I should mention the advantage of the approach that I use. The monopoles are playing an important role, and due to that, mesons that we get, they resemble the real ones. For example, adjoints and singlets in flavor group. In thin string regime, we observe the linear Raj trajectory starting from the very low spins. I remember that it's hard to remember. This was a work by Alexei Viktorovich with Professor Schiffman, where you've created the spectrum of massive states of hadrons, and red trajectories are linear there. So it's hard to implement it in theory when you have a thick soliton string, because you have a state with small spins. But still, in the thin string mode, everything is okay. And I would also like to say at once that baryon charge that we introduce is different from the baryon charge that is usually understood in quantum thermodynamics. Our theory, as scalar quarks develop vacuum expectation values, and if we would have a baryon charge, it will be violated. Therefore, the baryon charge is calibrated, and that's this U1 factor. And as for this baryon charge, that's a linear combination of symmetry and global U1 symmetry that is usually taken as baryon charge. So therefore it equals 0 for the first quarks. Then When we shift to strong coupling, in weak coupling we had screened quarks, we had these X bosons, what was already mentioned. When we shift to strong coupling, they no longer exist. In strong coupling, they break down into monopole and non-monopole mesons. And let's follow the temperature. In ordinary temperature, supersymmetry is violated, but as for subsymmetry, temperature, I believe you referred to compactification. And supersymmetry here is not violated, and that's an interesting goal. And here we can refer to the recent works who worked in separant mills, and they have certain results. When you compactify, you get into 3D theory, and they say that they can connect this Polakov confinement with other theories, with SW. Certainly it would be interesting to check it within the framework of our approach, and it's interesting to summarize the theory for quark cases. And I believe I mentioned everything because there were a lot of interesting comments. Victor, are you satisfied? Yes? Well, nearly, but not fully. I believe because one question was not answered. So you have a weak bond, weak coupling. Don't talk to me about the strong coupling. So we are working with a weak coupling. In weak coupling, we have a Higgs condensate from quarks. And monopoles in such condensates do not fly out. So they're confined. As for particles like boson, it's unclear. They lose their color by this expectation value. They don't have any other quants, and it's believed that they're confined as well. And as for the quarks, if we take ordinary superconductor, there are electrons tied in couples, and these electrons, if you smash them, they will fly out, and it's just the same here if you take quarks. There are no reasons for these quarks not to fly out. Suddenly, they will have zero color. Well, they are colorless. The average color equals 0. Because that's a Higgs event here. And as for baryon charge, it's correct to say that there is a certain other value for this baryon charge, because this baryon charge that we usually see, it flows out into condensate and it does not remain, but still there's yet another value that remains, this form of baryon charge and color. And this value is something that the quark used to have, and it remained. And as a result, you lose the particles that have its expectation values, and this does not happen in nature. The question is, do I get it right that here and in n equals 2 Seinberg model and in your other models, the colorless quarks fly out? Well, we do have them in weak coupling, and that's quite sad. Well, Victor, in Higgs phase, certainly the color is screened. and you can have whatever you like flying out. In Higgs phase there is confinement, and then people say that nothing happens, that Higgs phase is a confinement phase. They have nothing in between because they're just the same. Yes, because initially there's not just Higgs but also a linear potential. No color and flavor quants from color flavor locking mechanism. This screened quark has this adjoint representations. Yes, that's right. There's a combination that remains there from color and flavor. Yeah, okay, I get it. Okay. Yes, but it's not dual. Yes, it has a joint representation on all non-able. Yes, but in nature it does not happen. Well, I don't say that it's like in nature. Yes, that's why I wanted to mention this drawback, and certainly the candidate for the degree could provide an answer in his thesis. Yes, okay. But yes, certainly I should have covered it, but it's already thick enough, and therefore I did not cover this question as well. Yes, the thesis is quite a good one, Victor, and I also wanted to mention that because due to the fact that it's instead of confinement case, why don't you take that instead that's a case instead of nature? Oh yes, okay. Yes, we need to understand what's the difference with nature. Yes, certainly, but that's coupling. This is a coupling that is not that obvious. Instead of confinement, how can it be connected with what we observe? It's not. It does not look obvious. Yes, I've told you from the very beginning that there's no direct proof that in strong coupling we have a direct mechanism that is incorrect. It's really hard to prove. If you would have more experiment in the color sector, then yes. Yes, okay. Okay, now I'm satisfied with the answer. Okay. Okay, I'll give the floor to Sergei then. Professor Fonin. Yes, hello. I won't read out the entire text that describes the thesis. I don't need to explain that confinement event is one of the key ones, one of the key unresolved issues, and in this situation it's always important to have some models that can be resolved, in which you can analytically see what happens. And in this context, the approach of the thesis is quite a successful one, and it's justified because, as far as I know, in all resolved models in which you can analytically prove confinement in dimensions more than 2, it's based on the monopoles condensates. And that's it. Now, as for remarks, I have 4 of them, and 3 of them were already mentioned by Victor. But still, once again, I'll read them out. The first remark on the choral symmetry, that this thesis is not, this idea is not covered except for one phrase in conclusion on the interaction on the spontaneous violation of choral symmetry and confinement. The question is an important one, because, as it was already mentioned, it has nothing to do with n equals 2 supersymmetry theories, but if we talk about case when it equals 1, it becomes interesting. On the other hand, I would like to mention that that's an important and very hard issue that is still not resolved. I've seen a lot of works where people speculate on that, on choral symmetry and confinement, that there's a general agreement that one event can happen without another one and vice versa. But in models in which we can have both. There is no general picture how one can be connected with each other. What's the causation here? And second point is that the author is continuously introducing new ideas that are explained later on in the thesis, and it really complicates the reading. For example, paragraph 1.1 is titled, so you remember the title, but this theory is not defined. You don't give the Lagrangian there. You just write 4dn equals to super QCD. So you should describe it at once there. Third point, third remark, that was not mentioned. As far as I'm concerned, in the introduction chapter, the author did not demonstrate sufficient worldview in confinement and in monopole approach to describe this event. Therefore, it's unclear whether the author knows about the ideas of other approaches on the explanation of confinement of quarks and gluons, and can you see the advantages and disadvantages of your approach compared to others. So the thesis is quite volumetric, as it was already mentioned, more than 200 pages. So it's close to doctoral thesis, but it's written as a review, as a full technical description of the thesis. But thesis is much more than a review, and we expect to see certain comparisons in the introduction, because that's a qualification work. And we expect a more detailed introduction aimed at non-specialists in the field, non-specialists in this specific field. And that's it. And it was already mentioned in the text that we see some style problems, misprints. However, as far as I'm concerned, there are not many of them. So the general impression is not damaged by that. So the fifth remark, but rather author, you mentioned thin string and rich asymptotics. I haven't seen this part in the thesis, the description of this part. So that's an interesting field, because in real phenomenology, in real spectra of light, mesons and baryons, we do see a very quick yield to rich asymptotics in the spectrum. They are quickly becoming linear. That's to the question on the connection with real QCD, with real interactions. And according to numerous model assessments, this should happen asymptotically at high spins, so we don't have an understanding why it happens so quickly. And in your idea, you can explain that using your methodology, so it would be interesting to see your further work in this direction if it's interesting to you. Maybe you would explain it, how can it be connected? Maybe there is some general physics connected with real interaction. Why do you use this rich asymptotics? Why there is such a quick shift? That's not to the thesis, a remark to the thesis, but rather a remark for the future. But certainly it does not compromise the overall impression. And there are very good publications according to at the level of best world universities. Therefore, there are no doubts that Evgenii really deserves the degree of the candidate of sciences in physics and mathematics, in theoretical physics. And quite formally, the thesis meets all the requirements. That's it. Okay, will you answer? Yes? Indeed, I recognize that thesis looks like a theoretical review. Unfortunately, I understood it late when I read it in your review. For example, chapter 1, I did not even think about adding a Lagrangian there in chapter 1. Well, I worked on that, and for me, I'm quite familiar with these things for several years, and certainly I know them, but I didn't even think about mentioning them because I believe that everyone knows them. But then I remember that that's not my thesis supervisor and me who are going to read this work, therefore certainly I should have mentioned that. And in particular in the introduction, certainly I don't have a review of other mechanisms of confinement explanation. I'll mention several of them here in order to close the gap. Certainly there is a Abelian-Higgs model that resembles what we are working with, but in certain cases when monopoles are confined due to condensate in 1+1, we can mention a very important model, a joint QCD, and you see a lot of articles mentioned on different conferences with one major run of flavor, and if the flavor is a massive one, in theory we have a confinement, we can use a loop to demonstrate it, and so on. I didn't go into details, but I've heard several reports, and also Hooft model with fundamental heavy quarks. In classical formation, that's one heavy quark and one a light dynamic. In 2+1, we can mention Polyakov confinement, the first confinement that was demonstrated analytically in 3D. And as for 4D, we don't have numerous models here. There are no other models, in fact, that work directly with 4D Lagrangian. For example, there is a lattice in real QCD, but it's a numerical lattice. You should interpret the physics from these results. In this regard, our model has certain benefits, as I've emphasized. Our model here is, I believe, similar to others. What we study is that we study microscopy theory, and we also managed to do something. As for Rage trajectories, we don't mention that in the thesis, but still it was demonstrated not in the thesis but in the work of Alexei Viktorovich with co-authors. And there, as far as I'm concerned, these linear trajectories emerge because we have thin string there, thin string regime. Why this Rage trajectory becomes linear? Because when the string in Solton models, it's rather thick, and when we are working with high spins of quark, anti-quark, monopole, anti-monopole, and when the string is rather long and we have this Rage trajectories, when we work with the small spins, the string does not resemble a string, it rather resembles a kind of combination, a kind of glue-on ball. And the string is always thin, even in a strong coupling. Therefore, certainly there is a Rage trajectory there. I have certain ideas how to study it later on, but not within the framework of this thesis. That's it, I believe. Okay. So are you satisfied? Yes, fully. And I would add that the lattices, what they see confinement, the picture of confinement strongly depends on the calibration. And there's a certain conference on the topic. Some see monopoles. In other calibration, they see central vortexes that are responsible for confinement, and they try to pick these configurations, and the linear growing potential is eliminated. So the lattices, you know, that's a black box, kind of black box. I don't believe that we'll understand it from the lattices analytically. Okay, thank you very much. You've fully demonstrated that you know other confinement theories as well. Thank you. Okay, then my review. Well, certainly I won't read it out fully, because here I list the basic results. And I would like to mention that in the thesis we have a lot of interesting and impressive results. And I mentioned them. And as for drawbacks, I have just some ideas for the future. I can't say that, considering the volume of the thesis, you could say that these are drawbacks. But there's one idea that I want to read out. The thesis mentions that monopole confinement in n equal 1 supersymmetry QCD is something that we observe in a case when quark masses are the same in the model. So I would like to learn whether it's possible to summarize these results for unequal quark masses. So that's a kind of drawback that I want to mention. However, it does not compromise the overall high value of the results that Evgenii received in the thesis. Okay. The thing is that indeed, as I've mentioned, when we violate supersymmetry in the model and we shift to N1, it turns out that monopoles survive in case when we have equal quark masses. If masses differ, we have an additional potential that damages everything. And it should be recognized that it's not obvious how these developments be summarized, can be summarized for different quark masses. But overall, it's surprising that monopoles survive regardless of this case, because half the polyg of monopole is connected with A3 with adjoint scalars that develop certain vacuum environments. And when we get to n equal 1 margin, you remember what happens. Quasi-classically, we could have expected that they will be completely eliminated. This monopole mesons, we could expect that they will just fade away, that they are going to collapse, break down, and that's it. And we'll get bosons, W bosons. But this does not happen. And that's a surprising fact. As for unequal quark masses, we should have to work a lot in this QCD, not just on the quark masses. Certainly we are going to think how to cope with these problems. Okay, thank you. So there's this formal wording that I want to read out. The thesis by Evgenii Ievlev, titled The Dynamics of Non-Abelian Strings in Supersymmetric Gauge Theories, meets the requirements of the orders of September the 1st, 2016, on the procedure of granting academic degrees at St. Petersburg State University, and Mr. Ievlev deserves the academic degree of the candidate of sciences in physics and mathematics in specialization 010402. Theoretical physics and Article 11 of the above-mentioned order is not violated. So, dear colleagues, is everyone satisfied with the answers? Well, yes, I've already mentioned I'm fully satisfied. Yes? Yes? No objections about that. Okay. Then I would like to give the floor to people who are present at the defense, not the members of the board. 2 minutes per anyone willing to ask a question. Does anyone want to speak out? No one? Okay. Then I ask the coordinator to help me. Did we get any questions submitted online? During the broadcast? No. No questions. Okay. Then I give the floor to the thesis supervisor. Alexei, please. Alexei? Yes. Yes, here I am. I'm once again fighting with the microphone. Okay. Certainly I won't read out my review because I have just 3 minutes. According to the schedule, I'll just say a few words. Before Evgenii joined our group, there was not just the discovery of non-able strings. Together with Mr. Schaefman, we found this instead of confinement phase in case when n equals 2 and screened quarks as well as gluons in weak coupling. They break down, or rather shift to monopoles, anti-monopoles, couples connected with confined strings. And the role of constituent quark in this phase is played by the monopole. So that's a kind of a novel phase. Previously people thought that calibration theories can be in Coulomb phase and a Higgs phase, and in our case we found it out in the quark vacuum, this fourth phase. N equals 2 QCD is really a field that provides a lot of possibilities for study. And an important, interesting question here was that in n equal 2 we have it, but does this mechanism instead of confinement survive if we take n equals 1? And we didn't get the final answer, but Evgenii's thesis gave us a lot of results on the topic, and it answered the main question: what happens with non-able instruments in this mu deformity when adjoint materials change mass when we go down to infinity with it. And the central question is whether monopoles still remain. And Evgenii mentioned that quite well. Therefore, I'll say that classical, certainly they shouldn't have remained. They should be eliminated. And indeed, it turns out that at large n's, this 2D theory is resolved at the world sheet, and we discovered 4 phases that differ in these transitions, and they collapse and eliminate and fade away. And in strong couplings, they still remain, and that's quite an unexpected result. And it really gives us hope that this instead of confinement mechanism may work in an equals 1 QCD. And Seiberg-Witten mechanism cannot be analytically traced when we increase mu. If you introduce the adjoint mass, at once you find out yourself working with a weak coupling. So saying that this mechanism works is something that we can't do. So these are kind of speculations. So the situation is better here. Yet, The articles that the thesis is based upon is written in co-authorship with Alexander Gorsky, Mr. Schiffman, and others. And in these works, the role of Mr. Ievlev was important and key. One, he has this physical intuition. He can apply complicated methods to resolve the set goals. Overall, the thesis is a fundamental study and the results are novel and original, and they are published. They were timely published, and certainly it meets the requirements to the PhD works, and certainly Mr. Ievlev deserves the academic degree of the candidate of sciences in physics and mathematics in theoretical physics. Thank you. Thank you, Alexei. As we hold our session with participants that have remote access, I would like to ask the members of the board if there are any questions, or maybe anyone present or our candidate for the degree. Does anyone have any questions connected with our work in the remote mode? If there are any, please feel free to ask. Okay, no questions. Distinguished colleagues, if anyone is willing to speak out among the members of the board, among anyone present here at the session, maybe there are other questions submitted? No? Okay. Then we stop the discussion. And it's 11:26, and we now shift to the voting procedure. So, distinguished colleagues, now I have an opportunity to hold a closed meeting when the broadcast is turned off. How do you think? Do we need such a discussion? No, I don't need one. Not me. Well, the discussion was quite specific, therefore I believe there's no need for that. Okay. Okay, we continue. Let's shift to the vote. So I kindly ask you to turn on the microphones, and I kindly ask to check whether we all hear and see each other. So please, dear colleagues, confirm. Yes? Yes? Okay. Then I raise a question on the award of the academic degree of the candidate of sciences in physics and mathematics and specialization in theoretical physics to Evgenii Ievlev. Professor von Stein, what's your opinion? As I've already mentioned in my review, I have no doubts that Evgenii Ievlev deserves the academic degree of the candidate of sciences in physics and mathematics in theoretical physics. Okay. Professor Novikov. Yes, no doubts about that. Certainly he deserves the academic degree. Okay. Professor Petrov. Yes, certainly the thesis deserves that. Yes, and the candidate also deserves this academic degree. Sergei, what about you? Yes, I believe so. So my opinion is just the same. support the award of the academic degree to Evgenii Ievlev. Thus, I would like to announce that out of 5 participants, we have 5 people who voted for the award of the academic degree, no one voted against, and no one abstained from the vote. So we decided to award the academic degree of the candidate of sciences in physics and mathematics in specialization 010402 theoretical physics to Evgenii Ievlev. Distinguished colleagues, due to the fact that our session is held remotely, I would like to ask if the members of the board have any questions on the procedure of this session. I would just like to mention that we are working remotely not just in space but also in time. Okay, now I'd like to give the floor for the finalizing remarks to Mr. Ievlev. Well, in conclusion, I would like to thank everyone. First of all, my thesis supervisor, Professor Jung. I hope that we'll continue working together, who managed to tolerate all my traits of character, but finally it all worked well. I hope that it will continue like that, and I would also like to thank the members of the board for the fact that they agreed to participate in the session, that they read the thesis, wrote the reviews, quite interesting ones. And I would also like to thank Professor Schiffman and Gorsky, whom I worked with on my articles. And certainly I would also like to thank all my friends who came to support me, who are watching the broadcast. And certainly I would like to thank the organizers of this session. Okay, that's it. Okay, let's congratulate him. Okay, and we therefore close our session. And I thank everyone for taking part in it.